gravitational wave astronomy, not just LIGO, but other frequency bands, 4 different frequency bands that we will open up. Well, 4 total frequency bands we will have open by probably the mid-2030s. I can talk about black holes. We can talk about wormholes. I can talk about why time machines self-destruct if you try to activate one, probably, and why it's only probably, not definitely. I can talk about neutron stars, quasars, sort of most any topic. I will tell you if I don't know. I have no shame about saying I don't know. But I would like to respond to your questions and let you guide the discussion rather than my trying to do it. So let me see if I can throw it open and we can get started. And don't be shy, there are no stupid questions. There are only stupid people who fail to ask the questions that they think are stupid. So please, let's begin back there.
Is it possible to arrive to the point faster than light?
Yes, I can travel from here to you faster than light. If the light has to go out to out to Mars and then back and bounce off a mirror on Mars. So it's an issue of routes that are taken by the light and routes that are taken by me. If you have a wormhole that leads from here to some distant place in the universe, which probably we can't have, but if you have one, then yeah, you can get there a lot faster than the light that travels through the external universe. The thing that is an absolute, so another example is the universe is so large that there are pieces of the universe that are beyond what we call our cosmological horizon. They are moving away from us faster than the speed of light, which is why we can't see them, because they're moving away so fast. And that does not violate the principles of relativity, because what the principle of relativity says is if you have 2 objects that are close enough together that there is negligible curvature of space and time between them, so that space and time are flat, they are like you have in special relativity, Minkowski space-time, in the region of those objects, then they cannot travel faster than the speed of light relative to each other. It's only then. If there is a lot of curvature of space and time, space and or time, in the region you're talking about, then standard speed limit doesn't hold. Yeah.
I've read the book of Stephen Hawking, and where
can you hear his question?
Yes.
Speak louder.
There's a chapter where Hawking talks about the travel in time, and there speaks mostly about ideas of yours. And I would like to ask you if you could like tell us more about something that I didn't understand very much, because it was much technical, too technical for me. But the part that I understood was that you needed to like grab the space-time to make a bubble to travel in time, travel back in time, and you needed the density of negative energy or something like that I didn't understand very much. If you could give an idea.
So the question is, under what circumstances can you travel backward in time?
Yes.
So just as there is an absolute speed limit when objects are close enough together that there's no significant curvature of space-time between them. Similar, we know, an absolute limit on not going backward in time in the following sense. That if you are side by side with somebody else, you experience the forward flow of time in the same way. And it's impossible for one of you to move forward in time, the other one to move back. Or another way to say it is you cannot move backward against the local flow of time. The local flow of time is like the flow of a river that's flowing so fast you can't swim it upstream. Nobody can swim upstream. On the other hand, if you have a river that has a side estuary, a region where the water goes in, it slows down, maybe it circles around a little bit, and it might join on to another piece of the river that's farther upstream. So basically you go out into another region, you can come back onto the river and maybe higher up on the river than you were. And so in a similar way, the only possibility for going backward in time is to go out in space and then return to where you started before you left. You can't sit here and go backward in time relative to other people who are sitting. And so the question is, then, can nature provide a route where you go out in space and come back before you started? And one conceivable way is with wormholes. I've described various things that I've written. That you have two mouths of a wormhole. You go in here, you come out there, but you come out of that mouth of the wormhole before you went in. You can come back and meet yourself and tell yourself it was not a pleasant trip and don't go. So that's one way, but it's also conceivable. So it's very unlikely that, it's quite unlikely that wormholes can exist, but not completely forbidden. It's also conceivable, but not very likely, that our universe has a structure whereby you can go out into our universe and come back before you left. And that has to do with what is the structure of space and time out there. Does our universe have what we call closed time-like curves, which just says you can go out on some curve in the universe and come back before you started. So those of you who've seen the movie Interstellar, which is another thing I'm happy to talk about. In the movie Interstellar, Cooper never goes back in time. He's always moving forward in Earth time. Let's move that way in Earth time. And he sees his daughter, much younger, after he's gone on his trip, and he's behind her bookcase. He sees her much younger. He is in one face of a tesseract, a four-dimensional cube. She is in another face of the tesseract. This tesseract is constructed by a very advanced civilization that lives in the bulk in the fifth dimension. It's constructed in such a way that it takes a long time for the light to go from his daughter through the successive faces of the tesseract to him. So he sees his daughter when she's very young. The light took a long time to travel along this route. But on the other hand, in the fifth dimension, in the interior of the tesseract, there are closed time-like curves, and that's the way these bulk beings build it. But you and I as human beings can't go into the fifth dimension. We can only live in four dimensions, three spaces at one time. But gravity is the one thing that can go into the fifth dimension. And gravitational forces in this movie, this is the backstory, travel that when he pushes on sort of a lever thing, it creates gravitational force that travels backward in time in the interior, in the five-dimensional interior, and goes back and pushes on the second hand of the watch of his daughter. So he's signaling backward in Earth time by way of these closed time-like curves, because this region with so-called closed time-like curves has been built and engineered by the engineers of the bulk civilization. This is actually told to you. If you're a real fan of Interstellar, you go back to when Cooper, Matthew McConaughey, and Anne Hathaway are sitting in a Ranger space shuttle between giant waves on the water planet. And they have a conversation in which she talks about, to them, the bulk beings, if you go forward, time is like a mountain, you can climb up and so forth. to the bulk beings if you can be in the fifth dimension. So the explanation, for those who are puzzled by the ending of the movie, the explanation is in her dialogue in between waterways on the water. This is a side remark, but for those of you who love Christopher Nolan's movies and are always puzzled by things, generally the explanation for something that puzzles you is in dialogue at some totally different location in the movie. This is the secret of trying to understand Nolan's movies, like Memento and Inception. Anyway, so that was off the track. But the key thing then is that Interstellar gives you an example where there is a region where there are closed time-like curves. You can send something in there, but in this case, it's in the fifth dimension. We can't do this, but the gravitational forces can go through the fifth dimension, go backward in time. But the universe has to somehow provide you with the region with closed time-like curves. You always have to go out and come back. That's the only possibility. So then the issue is whether or not the laws of physics permit such reason to exist, or permit a very advanced civilization to engineer such a region. And that's where we don't know. Stephen and I both, and our students worked quite hard on this issue in the early 1990s, late 80s, early 90s, and came to agree that on two things. First, that when any advanced civilization builds something that's has a possibility to be a time machine, when it's first turned on, because to travel backward in time you must go out in space and come back. There's a first thing that can make that trip. It's the stuff that travels the fastest possible, which means light or vacuum fluctuations of light. The key thing about vacuum fluctuations is they cannot be shielded out. You can't block them. Very high frequency vacuum fluctuations. So the first thing that will travel backward in time will be some very high frequency vacuum fluctuations that you cannot shield out. They'll go around, come back, and arrive back where they started and pile up on themselves. So you now have twice as much vacuum fluctuations to return to right where it started. And then it happens again and again and again, and you have an explosive growth of vacuum fluctuation energy, which turns into non-zero renormalized energy, for those who know about, or know the buzzword renormalization in quantum field theory. It becomes non-zero, and the issue is whether or not that explosive growth of this energy circulating through the time machine, going out in space and coming back, does that explosive growth get strong enough to destroy the time machine? And that's where Stephen and I struggled with this. I thought it didn't. He convinced me that it might, and we convinced each other that we don't know the answer until we master the laws of quantum gravity. The same laws of quantum gravity that control the birth of the universe, control what goes on in singularities inside black holes, the quantum data that Cooper is searching for in Interstellar. These laws of quantum gravity also control whether or not time machines self-destruct by this explosive mechanism. That's a long answer to your question. I try to describe that answer in my book on the science of Interstellar. And probably do a better job there probably than in earlier books. It's also Stephen and I have this book, The Future of Space-Time, that we both wrote essays for, and Igor Novikov wrote 3 essays on time travel, in which Stephen and I both talked about this.
Is it possible to have a bullshit gravity force? And if so, what does it imply?
So in some sense, the accelerated expansion of the universe is due to a repulsive gravity force. The universe, you have a lot of mass in the universe. It ought to be pulling on each other, and so it ought to be slowing down the expansion of the universe. And it was a tremendous surprise when it turned out to be speeding up. The laws of physics, if you dig into them, say that this is possible if you have what Einstein called a cosmological constant. what I would say it violates certain energy conditions. You have negative energy. Well, let me start again. You have negative energy plus pressure as seen by some observers, basically. And so negative energy, negative in some carefully defined sense, can cause repulsion, gravitational repulsion. We do see such gravitational repulsion in the accelerated expansion of the universe. So the question then is, if you want to build anti-gravity machines, can you collect enough negative energy locally in your vicinity to make a successful anti-gravity machine? And again, well, that's not one of these questions that I dug into myself in detail. I don't know the real answer at this point, but by and large, the answers to these kinds of questions are we don't know, but probably not. I'm not sure about that. It is common in high precision gravity experiments to be in a situation where you do not want to have any stray gravitational fields aside from the pull of the Earth. More precisely, you don't want any gradients in the gravitational field. You want the gravitational pull to be identical here and there. So if you have two freely falling objects, they don't feel gravity. They're moving side by side. They're not being pulled together or pushed apart. So no tidal gravitational forces. And you can do that by taking big masses and positioning them appropriately around the region of interest. You can get rid of all the tidal gravitational forces and have to whatever accuracy your techniques allow, have a region with truly uniform gravitational field that you can then annul by just falling freely. You see no tidal forces or anything. And you need that kind of thing for some kinds of experiments, such as an Utfish experiment, trying to test whether the inertial mass and the gravitational, whether the two masses, whichever they are equal, to test whether or not things fall toward the sun with the same gravitational acceleration, basically, independent of their chemical composition. And so annulling gravity in that sense of getting rid of tidal gravitational forces is a parcel of, it's a piece of modern experimental technique in gravity experiments.
Could you explain very roughly what is the information paradox in black holes?
So the information paradox is a phrase that is used, not a very good phrase, to describe an issue in quantum mechanics. In quantum mechanics, the standard way that quantum mechanics is formulated in terms of Hamiltonians and the Schrödinger equation and so forth. Evolution is always unitary. And the unitarity of evolution is key to the whole structure of the quantum mechanics. And if you're dealing with the entire quantum mechanics system, if you deal with a piece of the quantum mechanical system, then you can have non-unitary evolution because of quantum correlations or entanglement that's built up between your region and another region. But in the absence of that kind of entanglement, you have unitary evolution. So Stephen Hawking in 1975, this is soon after he discovered Hawking radiation, calculations, idealized calculations he did for properties of black holes. He did a calculation that concluded that the radiation that comes off of the black hole, Hawking radiation, due to quantum effects of black holes, is always perfectly thermal. Which means basically perfectly random. So it contains basically no information. And so then he said, look, if I make a black hole by imploding a star or anything else, there's all the information about what went into the black hole that has gone in there. And all that comes out is thermal radiation. He said the evolution will be non-unitary. There's no way